In this video, we want to look at continuing to talk about bonding, and this time we're going to talk about bonding through the use of hybrid orbitals. Now, when we think about trying to describe a bond, and bonds exist in all of our molecules, the easiest way to describe that bond is an overlap of orbitals. One orbital from each of the atoms that are involved in the bond. We would call these atomic orbitals. And we would say that the region where the orbitals meet, where they overlap, is where the electrons are being shared at. There's a little bit of a problem with this way of describing bonding, though. And the problem exists in that the simple overlap of atomic orbitals cannot accurately describe the bonding that's occurring within these molecules. And we can use a molecule that we've already have dealt with in terms of writing Lewis structures, talking about VSEPR, and that molecule would be CF4. If we think about CF4, if we only try to describe the bonding in that CF4 using atomic orbitals, we're going to have a serious problem. Because if we only use atomic orbitals, you have s orbitals and p orbitals. And we know that the p orbitals are 90 degrees apart from each other. Well, if they're 90 degrees apart, how can you get what we actually have for the bond angles? Remember, when we have CF4 on the right, we have the Lewis structure. And we know with 4 electron groups, it's a tetrahedral electron pair geometry. Well, those angles are 109.5 degrees apart from each other. That angle from fluorine to carbon to fluorine we've seen is 109.5 degrees. You can't rationalize that just with the atomic orbitals and those p orbitals that are 90 degrees apart. So what this shows is that we can't just use atomic orbitals to describe the bonding. This is where hybrid orbitals are going to come in. So when we think about hybrid orbitals we can use to successfully explain the bonding in our molecules. And the way we want to think about hybrid orbitals is we want to think about hybrid orbitals as linear combinations. That's kind of fancy math language for averaging of the atomic orbitals. Not averaging like you would average a set of numbers, 2, 4, 8, 7, 5, not averaging in that type, but when we talk about linear combinations, what we're talking about is kind of an averaging of the equations that describe those shapes. So here are guidelines for creating these hybrid orbitals, and then we'll do a bunch of examples that use these guidelines. And the first guideline says is the number of electron groups determine how many hybrid orbitals are needed. And for this, remember, you need to use the VSEPR counting, where if you have a multiple bond, a double bond, or a triple bond, it will only count as one electron group. So how many hybrid orbitals you need, that goes back to the number of electron groups that you have. Then once you've determined how many hybrid orbitals you need, you can go into the second guideline. However many hybrid orbitals you need determines how many atomic orbitals need to be used in their creation. So if you have 3 electron groups, you need 3 hybrid orbitals. That means you need to start with 3 atomic orbitals. And the third guideline says that the identity of those hybrid orbitals is determined by which atomic orbitals were used in order to create them. The end result is going to be based upon what you kind of started with at the beginning. And we're going to use these three guidelines for each of the different types of hybrid orbitals, and we'll see these guidelines being used in action. So the first what we want to think about is what happens if you have two electron groups. That's the smallest number of electron groups that we can have. And for this, we're just going to go through these guidelines and kind of think about that sequence of generating these hybrid orbitals. And what are they? Where did they come from? Well, the first guideline says if you have two electron groups, that means you need two hybrid orbitals. So I'm going to represent orbitals with boxes here. And I need to make two hybrid orbitals. That's the first guideline. That's all it's saying is that two electron groups, we need two hybrid orbitals in order to represent them. The second guideline says, well, if you need two hybrid orbitals, you're going to have to use two atomic orbitals in their creation. So on the left here, I'm going to start with my two atomic orbitals. Again, the boxes are representing those orbitals. Now, which atomic orbitals am I going to use? Well, we always start with the s orbitals, so we would have to use an s atomic orbital, and we would also have to use a p atomic orbital. So we're going to take that s orbital, we're going to take that p orbital, and then we're going to go through this process of hybridization, taking the linear combination. Now we're on to that third guideline. What is the identity of those hybrid orbitals? Well, these hybrid orbitals look like if you took an s and a p orbital and mixed them together. So this type of hybridization we refer to as sp hybrid orbitals. And these two hybrid orbitals would be identical in size and shape, and they're going to be arranged in a linear geometry, kind of matching what we know happens when we have two electron groups. Now there's something important to kind of take note of this when you're looking at this. We know that when we have the atomic orbitals, there are three different p orbitals that we have. We only used one of them. That means we have two of those p orbitals left over. That's going to become important later. We can see what we can do with them. But for right now, we just want to kind of make note that I have some p's in reserve. They weren't used in this hybridization. That's what happens with two electron groups. We're going to do the same thing when we're looking at three electron groups as well. So when we're thinking about three electron groups, we're just going to use those same guidelines again. Three electron groups, the first guideline says if we have three electron groups, then I had better have three hybrid orbitals. We'll represent those with boxes. Second guideline says however many hybrid orbitals you have, that's how many atomic orbitals you need to use in order to create those hybrid orbitals. So if I have three hybrid orbitals, I need to start with three atomic orbitals. Now, what atomic orbitals am I going to use? Well, I'm always going to start with the s, and then I'm going to go to the p's. I'm going to use an s and two p atomic orbitals. What am I going to do? I'm going to take that linear combination, I'm going to hybridize those, and what's the result? Well, the result of those three hybrid orbitals is they'll all be identical in size and shape. What will they kind of look like? Well, they look like the combination of an s and two p's. So we call this type of hybrid orbital sp2. So these are sp2 hybrid orbitals, or we have sp2 hybridization. Now, again, these sp2 hybrid orbitals are going to be arranged in a trigonal planar geometry. Have those 120-degree separation between each of the orbitals. Again, just like we saw in the last case, we know we have three total atomic p orbitals, and we only used two of them. We held one in reserve. We didn't send one into the mix of being hybridized. That means we have one p orbital left over that is going to remain unhybridized. Just what we did with 3 electron groups, we're going to do with 4 electron groups as well. So again, we're just going to use those guidelines now for 4 electron groups. That first guideline says, however many electron groups you have, you need that many hybrid orbitals. So 4 electron groups means I need 4 hybrid orbitals. Second guideline says, however many hybrid orbitals you have, you need to use that many atomic orbitals. So 4 hybrid orbitals had to come from 4 atomic orbitals. Which atomic orbitals am I going to use? Well, I'm going to start with the S, and then I'm going to use the P's. I'm going to send those in, hybridize and take that linear combination. Out are going to come those 4 hybrid orbitals. Their identity, that third guideline, is based upon what was used in their creation. So we used an S and 3 P's. So we call these type of hybrid orbitals sp3 hybrid orbitals, or sp3 hybridization is what you get out of this. And again, these 4 hybrid orbitals are going to be arranged in that tetrahedral geometry. They're going to be spaced apart 109.5 degrees like we saw in the Vesper. Same thing that happened with 4 electron groups is going to happen with 5 electron groups. We're dealing with 5 electron groups. Well, that first guideline for hybrid orbitals is going to tell us 5 electron groups means we better have 5 hybrid orbitals. 1, 2, 3, 4, 5. So second guideline says number of hybrid orbitals you have to start with that same number of atomic orbitals. So 5 hybrid orbitals means we better start with 5 atomic orbitals. What atomic orbitals am I going to use? We'll start with an S, then we go to our P's. We have 3 P's, and you see we're out of P's. So what comes after a P orbital? Well, then we would have to start getting involved in using d orbitals. So we'd use an s orbital, 3 p orbitals, and a d orbital. We would send them in to the linear combination, make those hybridize. We'd get 5 hybrid orbitals coming out. The identity, that third guideline for these hybrid orbitals, their identity is based upon what atomic orbitals was used to create them. We would call this type of hybrid orbital sp3d hybrid orbitals. So these would be sp3d hybrid orbitals, or sp3d hybridization. And these sp3d hybrid orbitals, how are they situated in space? Well, they're situated in space in an exact matching fashion to that trigonal bipyramidal geometry. You're going to have 2 in the axial position, 3 in the equatorial position. You're going to have 90 and 120 degree bond angles. You're going to have that 180 degree bond angle in there as well. Now we do have d orbitals left over that aren't being used in the hybridization, but we're not going to use them for anything. So I'm not even going to talk anymore about those. Same thing is going to happen when we have 6 electron groups. We're going to use those guidelines the exact same way. 6 electron groups means 6 hybrid orbitals, so we'll get our 6 hybrid orbitals in there. Second guideline says number of hybrid orbitals tells you how many atomic orbitals you have to start with. So 6 hybrid orbitals means 6 atomic orbitals. We'll get those in there. Last step is to deal with the identity of things. Well, what atomic orbitals are you going to use? Well, we would start with S, then we would use P's. We have 3 p orbitals. We're out of P's, now we would have to start using d orbitals. So we'd use 2 d orbitals in there. We would take them, that S, those P's, those D's, take the linear combination of those, and out would come these 6 hybrid orbitals. What will be the identity of those 6 hybrid orbitals? Well, they would look like what atomic orbitals were used. So we would call them sp3d2 hybrid orbitals. So we'd have sp3d2 as our hybridization, or sp3d2 hybrid orbitals. These would all be the same size, the same shape. It would just be their orientation, their geometry. How would they be situated with respect to each other? Well, those 6 sp3d2 hybrid orbitals would all be arranged in an octahedral geometry. Those 90, those 180 degree angles, they would look just like that octahedral geometry we saw when we were dealing with VSEPR. So each differing number of electron groups matches a different geometry. We saw that in VSEPR, and now those specific geometries now match a specific type of hybrid orbital. 2 electron groups will always be sp. 3 electron groups, sp2. 4 electron groups, sp3. 5 electron groups, sp3d. 6 electron groups, sp3d2. So there are 2 different types of bonds we need to talk about. And this has to deal with how the overlap between the orbitals occurs. And for this, because we're a little bit more familiar with the shapes of atomic orbitals, I'll use atomic orbitals to kind of represent these differences. So there's 2 different types of bonds that can exist. The first type are called sigma bonds. See that with the Greek letter sigma, kind of looks like a O with a little bit of a tail. And in a sigma bond, the overlap occurs in the region of space between the 2 nuclei. The overlap is happening in that region of space directly between the 2 nuclei. So we can represent that with s orbitals like we see on the left. That shaded in red is showing the overlap of those 2 orbitals. And you can see that that overlap is happening between where the 2 nuclei are. We could also represent that on the right, a sigma overlap with some p orbitals kind of put end to end. Again, that region of overlap is shaded in red. That's happening between where the 2 nuclei are. So if that region of overlap happens in the space between the 2 nuclei, we would call that a sigma bond. Now there's another type of bond that we could have. We could also have a pi bond. In a pi bond, this overlap occurs in the region of space, not directly between the 2 nuclei. And for this, we can see this with p orbitals. We kind of stand 2 p orbitals kind of standing up vertically, kind of running that up and down direction, and we overlap them. The overlap, we can see our overlap here. Our overlap is where the red is again. The overlap is not directly between the 2 nuclei. It's in a different spot. In this case, it's above and below where the 2 nuclei are at. That region of space between the 2 nuclei, there's no overlap there. You don't see anything. The overlap is occurring above and below. So we have these 2 different bonds, sigma and pi bonds, based upon how those orbitals are overlapping with each other. And to talk about these pi bonds, we can be a little bit more specific. Pi bonds come in two different types. They're called localized and delocalized pi bonds. And we want to talk about the differences between them. In a localized pi bond, the electrons are just being shared between two atoms. And you can know that they're just being shared between two atoms because you will not see any resonance structures. No resonance structures are going to be present. So if we look at the example molecule that we have, CH2O, one of those bonds in that double bond between the carbon and the oxygen is a pi bond. And there's no resonance structures involved with that. We could not write any resonance structure for this molecule. That means those electrons are just being shared between the carbon and the oxygen. The other atoms are not involved. So that's delocalized. There are no resonance structures in play. If you have delocalized, in a delocalized pi bond, the electrons are being shared between 3 or more atoms. And you'll know you're in this situation because there will be resonance structures. And kind of our classic example we've been using for resonance structures is SO2. So I have the two resonance structures of SO2 on the bottom, and you can see with the resonance structures, the double bond appears to be switching, but we know that it's not switching because it never looks like A and it never looks like B. It always looks like an average of that. What does that mean? Well, that averaging of that means that those pi electrons, that pi bond that we have, is not localized. It's spread over the entire surface of that molecule. And that kind of helps explain why resonance structures are an averaging of things. The actual molecule of SO2 does not look like A. It does not look like B. It's always going to look like an averaging of those two structures because those electrons are not set. They're not defined in one locality. They're spread over the entire molecule. To kind of give you a kind of idea of where that sharing occurs at, for our formaldehyde example, CH2O, we can see that that sharing is just between the carbon and the oxygen, and it's happening above and below the plane of the molecule. It's not happening directly in the space between the carbon and the oxygen. In a delocalized pi bond, so here our example is HCO2 minus. Here in this delocalized pi bond, we can see there are resonance structures. So you can see A and B here. What this really is trying to show is that the electrons are really not set between two individual atoms. They're spread across all three atoms. Here, they're spread across the carbon and both oxygens. They're not set in one spot. That's why one resonance structure does not accurately portray the molecule. It's really an averaging of both or all resonance structures. Because of that delocalization, those multiple resonance structures are trying in a static image to express the idea that those electrons are not localized. They're delocalized. They're spread across several or many atoms. Now, what we want to be able to do is we want to be able to look at a molecule and in as much detail as possible describe the electrons in that molecule, describe the electrons in those bonds with as much detail as possible. Basically, we're trying to tell a complete story of all of the electrons that are within a molecule. And here's how we do this. These are the guidelines, and then we'll do a couple of examples that kind of show how this works. So first, anytime you see a single bond in a molecule, so a single bond in a molecule, we're going to describe as a sigma bond. Single bonds are going to be sigma bonds. And for sigma bonds, we're usually going to describe them as an overlap of hybrid orbitals. We're usually going to use hybrid orbitals to describe them. One hybrid orbital from each atom. Whenever you have a double bond or a triple bond, in that situation, one of the bonds is going to be sigma and the other ones are going to be pi bonds. In a double bond, you're going to have one sigma bond and the other one has to be a pi bond. In a triple bond, you're going to have one sigma bond and two pi bonds involved in that. And the reason being, if you have a double or a triple bond, you're sharing 4 electrons. Triple bond, you're sharing 6 electrons. You can't jam all of those electrons into the same region of space. That space between the nuclei can really only hold 2 electrons. So if you're sharing more than 2 electrons, that has to be in some region outside of that space, that area directly between the 2 nuclei. That's why in multiple bonds, a double bond or a triple bond, you only get one sigma bond, the other ones are pi bonds. When we have pi bonds, we want to talk about the overlap of unhybridized p orbitals. Remember, when we did the hybridization, for some of those hybrid orbitals, sp, sp2, we had unhybridized p orbitals that we didn't use in the hybridization. Those unhybridized p orbitals can be used to form these pi bonds. And we're still looking at one from each atom. And again, we just saw that pi bonds can either be localized or delocalized based upon if there are resonance structures or they're not resonance structures. In a localized pi bond, there's going to be no resonance structures. In a delocalized pi bond, we would have resonance structures. And the last thing we would do is we would talk about the lone pairs that exist in a molecule. Generally, for lone pairs, we're going to describe them as residing in hybrid orbitals. So these are the guidelines. Now we're going to do a couple of examples where we're actually going to look at a molecule in as much detail as possible, describe what's happening with all of the electrons in that molecule. So here's our first example that we want to kind of talk about and do. And I kind of labeled all of the electrons. So the first sets we're dealing with are going to be those that are labeled A and B. It turns out A and B are the same. But what we're looking at are the lone pairs that exist on the chlorine. So how could we describe what's happening with those electrons in as much detail as possible? Well, we said that for chlorine, how many electron groups do we have? We have 4 electron groups. Those lone pairs are going to reside in hybrid orbitals. Well, we can be more specific than just saying hybrid orbitals. What type of hybrid orbitals? Well, we said there are 4 electron groups around that chlorine. 4 electron groups matches with sp3. So in as much detail as possible, we could say that for A and B, the lone pairs on the chlorine reside in sp3 hybrid orbitals. So that would be describing them in as much detail as possible. So now if we kind of continue looking at different electrons in here, the next set of electrons we would look at are those labeled C. So those electrons labeled C, here we're looking at the bonding between the carbon and the chlorine. So we're going to describe these electrons in as much detail as possible. Well, that bonding between the carbon and the chlorine is only a single bond. So what did we say happened with single bonds? Single bonds we want to describe as sigma bonds. But we can be more specific than just saying it's a sigma bond. We can say which orbitals from each atom are overlapping in order to form that sigma bond. So electrons labeled C are sigma bonds. Now let's describe what's happening with that overlap. So for chlorine, we already said what kind of hybrid orbitals we had. For chlorine, we said we had sp3 hybrid orbitals, 4 electron groups around that chlorine. How many electron groups on the carbon? Well, we only have 3 electron groups on the carbon. Remember, a double bond only counts as 1 electron group. So what type of hybrid orbital matches with 3 electron groups? sp2. So what kind of hybrid orbitals does carbon have? Carbon has sp2 hybrid orbitals. So we would say that the sigma bond between the chlorine and the carbon is the result of the overlap of the sp3 hybrid orbitals on chlorine with an sp2 hybrid orbital on carbon. And that's how we would go and explain that bond, those electrons, in as much detail as possible. So now we're looking at describing the bonding between the carbon and the oxygen, so D and E. So you notice between the carbon and the oxygen that we have a double bond. Remember, in a double bond, you end up having 1 sigma bond and 1 pi bond. It doesn't matter which one you call sigma, which one we call pi. I'm going to start just picking out one and referring to that one as the sigma bond. So those electrons labeled D, highlighted in green. So D, we said that one was the sigma bond. Well, we want to talk about what type of orbitals are overlapping. Don't just say it's a sigma bond. Don't just say it's hybrid orbitals. Be as specific as possible. What type of hybrid orbitals are overlapping? Well, we already said that the carbon had sp2 hybrid orbitals. Why? 3 electron groups. So this sigma bond is formed from the overlap of the sp2 hybrid orbital on carbon. And now what's going on with the oxygen? Look at that oxygen on the top. How many electron groups? Well, 3 electron groups. Remember, that double bond only counts as 1 electron group. So what type of hybrid orbital does the oxygen have? Well, the oxygen also will have sp2 hybrid orbitals. So when we're describing those electrons forming the sigma bond between the carbon and the oxygen, we would say that they result from a sigma bond that's formed from an overlap on the sp2 hybrid orbital with the carbon with an sp2 hybrid orbital on that oxygen. So those would be electrons D. Now if we look at electrons labeled E. So this would be the pi bond of the two. Remember, double bond, 1 sigma, 1's pi. We just dealt with the sigma. Now we would deal with the pi bond. So the electrons in E are a pi bond. Well, when we have a pi bond, we have to describe, is it localized or delocalized? So what we're asking is, could we have resonance structures for this? Are resonance structures a possibility? And the answer is no. If you tried to draw any sort of resonance structure here, it wouldn't be a very good looking structure. There are no resonance structures that you could draw for this. So being there are no resonance structures, this is a localized pi bond. So here we're looking at a localized pi bond. Well, for pi bonds, how do we describe that? Which orbitals are involved? Well, pi bonds, we said, usually result from an overlap of unhybridized p orbitals that weren't used in the hybridization. Because remember, carbon was sp2. What do we have left over? A p orbital. Oxygen is sp2. What do we have left over? A p orbital. So it's those leftover p orbitals, one from oxygen, one from carbon, that are overlapping to form that pi bond. So for E, we have a pi bond. It's localized. There are no resonance structures. And it results from the overlap of the p orbital on carbon with the p orbital on the oxygen. So our last set of electrons that we are looking at are those labeled F. Here, these are, I highlight these in red. These are the lone pairs on the oxygen. So lone pairs aren't involved in a bond. So we're not talking about an overlap between two orbitals or two atoms. We're just looking at that oxygen. So those labeled F are lone pairs, not being shared, belonging explicitly to the oxygen. But what type of hybrid orbitals are they in? We can supply that level of specificity. We already said that oxygen is sp2 hybridized from having 3 electron groups. What does that mean? That means those lone pairs reside in oxygen's sp2 hybrid orbitals. So this is how you can use those guidelines that we just talked about on the previous slide in order to describe in rich detail all of the electrons in a molecule. We're going to do one more kind of example. So let's look at one more example of describing the electrons in a molecule. And we'll start with the electrons that are forming the bonds between the carbon and the hydrogen. These are single bonds, so we would describe them as sigma bonds, and usually we would talk about an overlap of hybrid orbitals. However, hydrogen can't have hybrid orbitals. Hydrogen only has an s orbital. It can't hybridize with anything. So for this, we're locked in. We're forced to just saying we have hydrogen's s orbital. Now the carbon, we do want to describe as hybrid orbitals in terms of what's overlapping. And here that carbon has 3 electron groups, so that means it's sp2 hybrid orbitals. So we would describe the bond between the hydrogen and the carbon as a sigma bond resulting from the overlap of hydrogen's s orbital with carbon's sp2 hybrid orbital. So next we'd be looking at the bonding between the carbon on the left and the central carbon. And here we have a double bond. Remember, whenever we have a double bond, one of those bonds is a sigma bond, one of those bonds is a pi bond. So let's start with the sigma bond. Sigma bonds we want to talk about as overlap of hybrid orbitals. So what hybrid orbitals are overlapping? On the carbon on the left, it's the sp2 hybrid orbital. The central carbon has 2 electron groups, so it's sp hybridized. So that sigma bond between the 2 carbons is a result of the overlap of the carbon on the left's sp2 hybrid orbital overlapping with the central carbon's sp hybrid orbital. The other bond in that double bond would be a pi bond. So for a pi bond, we would describe as either localized or delocalized based upon the presence or absence of resonance structures. There are no resonance structures that you could draw here. That means it's going to be a localized pi bond. So we have a localized pi bond between those 2 carbons. Pi bonds we describe as an overlap of unhybridized p orbitals. So that localized pi bond is a result of the overlap of an unhybridized p orbital from the carbon on the left overlapping with an unhybridized p orbital from that central carbon. Now what we just described between the carbon on the left and the central carbon, you would get the exact same thing happening between the central carbon and the carbon on the right. So we're not going to go through and repeat that. It would be the exact same analysis. The next set of electrons we would need to look at then are the bonding between the carbon on the right and the chlorine. So this is a single bond. So whenever we have a single bond, we want to describe that as a sigma bond. Sigma bonds, we want to talk about the overlap of hybridized orbitals. So what kind of hybridized orbitals do we have? Well, that carbon on the right has 3 electron groups, so it's sp2. The chlorine has 4 electron groups, so it's sp3. So we would say that the bonding between a carbon and a chlorine is a result of a sigma bond forming from an overlap of carbon's sp2 hybrid orbital with chlorine's sp3 hybrid orbital. The last set of electrons we would need to look at are the lone pairs on the chlorines. It doesn't matter which chlorine we would look at because they're symmetrical. We look at one of the lone pairs on the chlorine and we'd say we're not talking about an overlap, we're just interested in the chlorine, but lone pairs reside in hybrid orbitals. So what type of hybrid orbitals do we have? Well, there are 4 electron groups around that chlorine. 4 electron groups is sp3. So we would say that those lone pairs reside in sp3 hybrid orbitals.